Okay, we will continue to part 2 of how to compute turbulent compressible flows and focus on the key steps required to get the simplest possible flow, that is a boundary layer on a flat plate. Let me start with a recap of the Rand's equations that we have already discussed before. We will start with the mass conservation equation written for the mean density, and I'm writing the equations in tensor form so that it is applicable to both 2D, 3D and special 1D flow cases. That's our mass conservation equation. Here is momentum written for ui tilde being the Favre averaged momentum equation. Rho bar u tilde I u tilde j dxj plus p bar dxi, writing these two terms together so that we can identify them as inviscid fluxes, equal to derivative the viscous terms dxj sigma ij plus tau ij. Sigma ij is a bar. I've clubbed Reynolds stress and viscous stresses together. The energy equation is a bit long. Time derivative plus convection term, pressure, work. On the right hand side we have the viscous effects, the viscous work, which is sigma ij again plus tau ij times u I tilde, derivative of this whole thing with respect to dxj. Let me make a bit more space so that I can write the rest of the terms. Okay, now we have two additional terms on the right hand side. One is the heat conduction term, which is kappa plus kappa T, turbulent, dt dxj, and the whole thing another derivative dxj. And a similar term we have for the turbulent kinetic energy, remember that the definition of E bar, the total energy, includes turbulent kinetic energy as well. So if there is any viscous diffusion of turbulent kinetic energy of this form, mu plus mu t by sigma k, sigma k is a model parameter, dk dxj, the whole thing derivative ddxj. It's a bit crowded here, but let me see if I can clear it up a bit and make better space so you can see. Okay, and let's place this term right next to it. Okay, pretty close. Here is my energy equation, all of it, with unsteady, convection, pressure, viscous work, conduction, and diffusion of turbulent kinetic energy, all terms together. Okay, next we're going to go to the K and epsilon equations in the K epsilon model. The K equation has this form: ddt of rho k. Then there is a convection term dxj. On the right hand side, we have the turbulent source terms tau ij t u tilde dxj minus, that's the production, minus dissipation plus the viscous diffusion term mu plus mu t by sigma k times dk dxj. This term, the last term, is similar to what I wrote for the energy equation, so you can look it up and confirm. The last equation is for epsilon, which is again has the familiar form of unsteady and convection effects. Then comes the production term for this equation, which is similar to what we have for the k equation, but is multiplied by epsilon over k, and we place a model coefficient or model parameter C1 for which the value would be given, and you can look it up in any reference. The dissipation term for epsilon is of the form of rho bar epsilon square over k, and it comes with the second model parameter C2. The minus sign says it's going to decrease. It will be a negative term in the equation, similar to epsilon in the k equation. And the last term is, as usual, diffusion, which is mu plus mu t by sigma epsilon, another model coefficient, dxj. Okay, so these are the typical or the general form of k and epsilon equations. You may find many variants of these in literature. If you look up different papers, different sources, many people have come up with modifications to these equations. They have introduced what are called damping functions. Let me write this. They have introduced damping functions, that they have changed coefficient, they have introduced even some additional terms, and they all come under the category which are called low Reynolds number variants of the k epsilon model. It turns out the equation that I've written is valid in highly turbulent regions of the flow, but if you come very close to the wall, the viscous effects become prominent. So turbulence intensity decreases, viscous effects become large, so the Reynolds number effective in those regions is lower, and it turns out that these equations have trouble computing the flow in such near wall regions, and for those regions they have come up with low Reynolds number variants with additional terms and other parameters thrown into these model equations. Okay, now we have a set of partial differential equations that we need to solve. Obviously, we need boundary conditions, so that is the next step. And here I'm going to give you a few representative boundary conditions, specifically those which are useful in computing a turbulent boundary layer on a flat plate. They come in essentially two categories. One is at the wall, which is a no slip wall, and the question is what happens to k and epsilon at the wall. It's kind of easy to see that k, which is defined in terms of velocity fluctuations u prime, v prime, and w prime, and um, at the no-slip wall, velocity goes to 0. The same is true for velocity fluctuations. U prime, V prime, W prime are all 0. So K is 0 at a wall, sorry, at a no-slip wall, Kw. Epsilon, on the other hand, turns out is not equal to 0. It has a finite value. If you think about epsilon as the dissipative effect, the friction effect that kills turbulent fluctuations, then obviously friction effects are high near a solid wall. And it turns out that there are ways to derive this, and I will give you one of the final answers, that you can write epsilon value at the wall as something of the form, it's a derivative of the square root of k with respect to the wall normal direction y computed at the wall times the kinematic viscosity. It comes with some there's some understanding and some amount of depth goes into it, which we are going to skip for the time being, and take it as given and use it in the equations and in our numerical calculations. The other set of conditions that need to be specified are in the free stream. To do that, we need values of k and epsilon in the free stream. K again is a measure of the turbulent velocity fluctuations. So if we have an idea that the free stream flow, for example, if we are computing a flow on a flat plate and it is placed in a wind tunnel flows have some small level of disturbances or fluctuations as in the test section, and that is measured in terms of what's called the turbulent intensity, and it is defined as U prime divided by U bar. It says what is the how small are the velocity fluctuations compared to the mean velocity, and let's say typical values are in the order of 1%. So the velocity fluctuations are 1% of the mean velocity, and they can be in the range of 1 to 5% or sometimes even lower than that, but 1% is a typical number which is used. So we use this to compute k, and I'm going to call it k infinity for free stream, divide by u infinity squared. K is velocity squared, u prime squared, v prime squared, so there will be a square involved, and this turns out to be in the range of 0.01, which is 1%, square of that in the range of 10 to the power of minus 4. So for a given free stream flow for which we know the Mach number, temperature, density, pressure, velocity, we know u infinity, we can calculate k infinity, which would be in the range of 10 to the power minus 4 times smaller than the velocity squared. Getting epsilon infinity, or the value of epsilon in free stream, is actually much harder. It turns out that there's no way to really get it reliably or measure it very easily. So one trick that people use is that we say mu infinity, which is the value of viscosity in the free stream flow, viscosity of, let's say, air. We say, what if the eddy viscosity was of the same order, let's say same order as the molecular viscosity. Now eddy viscosity we know is C mu rho k square by epsilon. Now everything is free stream value. So rho infinity, if it is given, rho is rho bar. K infinity, if we have computed using what we just showed earlier, we can, and mu infinity is a function of T infinity. This equation with C mu given as 0.09, I think we specified as a model parameter. This equation has only one unknown, which is epsilon infinity. So this can be computed and we can get a value. Now, how reliable are these values? This is just an approximation. It turns out that if you're computing a turbulent boundary layer on a flat plate or any geometry, the results that you get in a turbulent boundary layer are not very sensitive to these values as long as they are non-zero. If you specify k infinity and epsilon infinity to be 0, you would actually get a solution to the whole set of equations we wrote earlier, where k and epsilon will be 0 in the entire flow and you'll get a laminar flow field. So you need non-zero values of k and epsilon in the free stream to seed the flow with some disturbances, and then the boundary layer takes over and grows these disturbances and makes it into a fully turbulent boundary layer. So let me write this down. Turbulent boundary layer, TBL, is relatively insensitive to the exact value of k infinity and epsilon infinity. These are the values we have specified are approximate, so but the exact values do not matter so much. But what is important is that whenever you compute boundary layer on a flat plate or any geometry, very near the tip there will be a small region of laminar flow and there will be a transition region. The location of the transition point is sensitive to values of k infinity and epsilon infinity. But fortunately, for most practical applications, the laminar part and the transitional part is so small, maybe within a few percent of the plate it's over, and the rest 95 or 98% of the plate is a turbulent boundary layer which is insensitive to these values. So we are in good shape as long as using these kind of boundary conditions and getting reliable values. So now let's see what a turbulent boundary layer looks like if you do all things right and run a CFD code, and with the RANS equations and boundary conditions, you would expect to see a turbulent boundary layer, which, let me try to draw a picture of it. Let's make it a little larger because we need more space. We have drawn earlier, or in many places you will see that a turbulent boundary layer has a shape which is something like this. Free stream edge value at the top and the wall zero velocity. I'm going to change this picture by drawing it having y on the x-axis and u, or u tilde in this case, on the y-axis. Additionally, I'm going to make a change. I'm going to plot y on a log scale. So the x-axis is logarithmic. It turns out that if you do that, you see certain interesting properties of a turbulent boundary layer. And that happens to be, you can actually get a region of the boundary layer which follows a straight line on this semi-log scale. So let me draw the three parts to a turbulent boundary layer. The one that is for very low values of y, which is very close to the wall. Remember, y never goes to 0 on this scale because it's a log scale. U velocity is proportional to y. So it turns out that it behaves something like this. Let's do it a bit better. It behaves something of this sort. This line is u proportional to y. The next line that I've drawn is u proportional to log of y. So a boundary layer actually follows the linear, which is the linear part, which looks like which is the first curve initially. And then at some point it switches to this next curve, which is the logarithmic variation. It stays logarithmic for a while, and then it deviates from the logarithmic curve, and then at the end flattens out. The flattening part is the edge of the boundary layer. So now here comes the nomenclature. The region where u is proportional to y is called the viscous sublayer. The middle part is called the log layer, and the last part is called the outer layer or the wake layer, wake region. This is true for all boundary layers. You would always have a region which is very close to the wall, where turbulent fluctuations are very small, trying to meet the no slip condition at the wall. That happens to be the viscous sublayer, and viscous effects are large. They damp out the velocity fluctuations. Then is the log layer, which is where turbulence picks up and has a dominant effect, and the outer layer is actually large turbulent fluctuations towards the edge of the boundary layer. Now it turns out that this log layer, although looks fairly large on the scale, but being a logarithmic scale, this only is about 10 to 15% of the boundary layer thickness. The viscous sublayer is actually maybe 1 or 2%, very, very small. And the rest of it is the outer layer, which looks like a small region, but it covers a much bigger part in the physical range. Okay, so with this I will stop here and pick it up.